All right, let's do chapter 3, Law of Running, Energy Systems and Running Performance. This chapter is packed with information, and we're going to break this into 7 parts and go through types of fuel, how we store fuel. We'll talk about limits to endurance performance, factors that affect fuel use during exercise, how to maintain fuel during an endurance event. We'll talk about lactic acid, and then even training and detraining responses. This is a big chapter. And I have to say that I'm not a nutritionist. I don't have recommendations for nutrition other than talking about macronutrients, carbohydrates, fats, and proteins. And I also have to say that Tim Noakes, Dr. Noakes, the author of this book, has changed his perspective on what fuels people should be trying to use during endurance performance. In particular, he is a big advocate of using fats for endurance performance. Again, we're talking about performances that last maybe 2 hours, 3 hours, 10 hours, 15 hours. And we'll talk about this through this chapter, in that fats are a very efficient way to store chemical energy. And if we can tap into that aerobically, it makes a lot of sense. But I'll also say there's a lot of controversy in terms of how much fat should be used during an event versus during a regular diet. I'll try to talk about it and raise some issues, get you thinking about different types of fuels to use. The bottom line is we probably should train ourselves to be more metabolically flexible to use fuels besides just carbohydrate, and we'll talk about that. Okay, so let's start with just energy. What is energy? Energy is the capacity to do work. Work is applying a force over some distance. There's different forms of energy: nuclear heat, mechanical, chemical, light energy. There's my definition in the wrong spot there, but energy is the capacity to do work. The units of energy are joules. Now, work, from a thermodynamics perspective, is the transferring of energy from one object to another. Mechanical work is the application of force over a distance, as I mentioned. So work and energy actually have the same units, joules. And again, it's just a part of thermodynamics in terms of explaining this interplay between energy and work. Now, how fast we transform energy from one form to another, or from one object to another, is power, rate of work being done. Okay, now another parameter that we need to get comfortable with is calorie. We know calories are on the food labels of foods that we eat. Calorie is a unit of heat. 1 calorie is equal to 4,184 joules. That's a large calorie. All right, so there is some abbreviation issues in the nutrition world, but typically we talk about kcals instead of calorie, or capital C. A calorie is the amount of heat needed to change the temperature of 1 kilogram water, which is 1 liter of water, from 14.5 degrees Celsius to 15.5 degrees Celsius. Okay, that's what a calorie is. It's the amount of heat needed to raise water temperature, and specifically 1 kilogram of water, 1 liter of water, from 14.5 to 15.5 degrees Celsius. If the energy were released of a substance with a caloric value of 300 calories, that would mean the temperature of 300 liters of water would be raised 1 degree Celsius. Okay, that's what a calorie is. So when you look at a food label and you see calories on there, that's what it's telling us. It's a unit of heat, and it's a measure of how much heat would be released if we burned that food, and that would tell us how much water would be raised. So it's a nice way to talk about conversion of energy from one form to another, because that conversion of energy is never 100% from one type of energy to another, and the inefficiency of transforming energy from one form to another typically results in the buildup of heat. So food, again, from a non-nutritionist perspective, food is simply stored energy, stored chemical energy. For example, a piece of buttered toast has about 315 kilojoules, about 75 calories of energy. That's enough energy to jog for 6 minutes or bike for 10 minutes. It's also enough energy to light a 60-watt light bulb for about 1.5 hours. All right, the trick is getting the energy from the chemical state and transforming it to something for mechanical, for exercise, or to light energy, to light the light bulb. Okay. Now, how do we do that? Well, it's through the digestion process. So digestion is the process by which food is broken down mechanically, chewing, and chemically, even starting in the mouth with saliva, and then down into the stomach, in the gastrointestinal tract, and converted into absorbable forms. Okay, so there's a little cartoon here. Digestion begins with chewing, and then it begins with even saliva, some chemical, and then it goes down into the GI tract where more chemicals are added to digest, to break the food down into absorbable forms. All right, those absorbable forms that we're going to be talking about will be carbohydrates and fats. So digestion begins at the mouth. Even the esophagus does some mechanical breaking down of the food into the stomach. Some small molecules, for example, alcohol, can be absorbed into the circulatory system from the stomach. Small intestines, this is where the majority of digestion and absorption takes place. This is important to know because one of the big issues in endurance events is GI problems, gastrointestinal problems. And those gastrointestinal problems are typically in the GI tract. All right, so in the small intestines, the majority of digestion and absorption takes place here. Secretions from the liver and pancreas enter here. Carbohydrates, fats, and proteins are absorbed in the upper middle parts of the small intestines. The large intestines, cecum, colon, transverse, descending rectum. This is where we're going to see lots of absorption of water. Okay, so some real specific digestion processes happening along the way, from mechanical to chemical, where macronutrients are absorbed into the system, into the circulatory system, and where water is absorbed. This is in your book, just an illustration of the different digestion processes, from chewing to esophagus, some squeezing down into stomach, some absorption here of small molecules. Liver is right here. That's going to release substances to help break down the foodstuffs. Into the small intestines, where lots of absorption is going to take place of macronutrients. And then the large intestines, lots of water is going to be absorbed into the system from there. Okay, so a pretty complex system. All right, so let's talk about carbohydrate. Let's talk about types of fuel. Carbohydrates are composed of carbon and water, and there's 3 types of carbohydrates: monosaccharides, oligosaccharides, and polysaccharides. Monosaccharides are more than 200 different types of monosaccharides. We will mostly be talking about glucose, fructose, and galactose. Disaccharides are a combination of 2 monosaccharide molecules. For example, sucrose, table sugar, is glucose and fructose. Lactose is glucose and galactose. Maltose, glucose and glucose. Simple sugars, brown sugar, corn syrup. All right. Polysaccharides are 3 or more simple sugar molecules. These are starches, fiber, and glycogen. Okay, so our carbohydrates are pretty complex in terms of types. Ultimately, we're going to start talking about using glucose as a fuel, because that's the main substrate that things will get converted down to and broken down to, but everything needs to be digested ultimately to get to that glucose. So carbohydrates are absorbed, absorbed carbohydrates are transported to the liver, okay? Glucose can be stored as glycogen in the liver or transported to skeletal muscle via the blood system, a circulatory system, where it would be blood glucose. Once it's in the muscle and stored in the muscle, we call it muscle glycogen. And we have two terms that are good to know: glyconeogenesis, new formation of glycogen from non-carbohydrate sources, and glycogenesis, formation of glycogen from carbohydrate sources. Just like the previous slide, there's lots of different carbohydrates. Ultimately, we need to get it to glucose and then enter our energy pathway. Glycogen is the only form of carbohydrates are stored. Okay, that's important, and that's the part that we're going to use for fuel. Glucose is used by the brain, kidney, and red blood cells as a main fuel source. Glycogen stored in the liver can be broken down to glucose and delivered at a rate of about 10 grams per hour at rest and 60 grams per hour during exercise. Okay, this is really important. All right, so put an asterisk in your notes. Notes will continue to refer back to this 60 gram per hour releasing of glucose from the liver during exercise, because ultimately we're going to be talking about replenishing glucose or maintaining the right amount of glucose in the system. And one of the recommendations is to take in about 60 grams per hour of carbohydrate. Again, he's changed a bit on that, but this textbook and people still try to work in how much carbohydrate to take in during exercise, and typically that amount is the amount that the liver is releasing glycogen into the blood, where it's then blood glucose, and that blood glucose is delivered to the muscle and it's pulled into the muscle to be converted, broken down into ultimately ATP that's used for muscle contraction. All right, so 60 grams per hour released from the liver. All right, so glycogenolysis is the breakdown of glycogen to glucose. That's just a process. Okay, now there's a term that's used in this textbook, and it's really important that we know this term. So again, asterisks here: hypoglycemia. This means low levels of glucose in the blood. How does glucose get into the blood? Well, the digestion process gets glycogen into the liver. The liver will release glucose into the blood to deliver it to the muscle. Right? So if there's low levels of glucose in the blood, that means that either the muscle has taken up the glucose so fast that the levels in the blood are too low, or the liver is depleted, or there's something breaking down here between the liver and the muscle that prevents the glucose to be in the blood. The history of hypoglycemia, Noakes talks about this in the book. 1924 Boston Marathon, post-race blood glucose concentrations were decreased in all runners that they measured. Runners with low blood glucose levels presented with asthenia, pallor, and prostration. Okay, you look these terms up, that just means loss of strength, lack of color, absolute exhaustion. Okay, so if you have, what they were noting was people who were hypoglycemic, low levels of blood glucose. How do you get blood glucose? You do a little finger prick. You take a drop of blood and you put it on a test strip, and you put that test strip into a sensor, and that sensor tells you how much blood glucose you have in your blood. So the next year, they used a high carbohydrate pre-race, and they prevented much of the hypoglycemia for the runners that they measured. Another just history point here: Harvard Fatigue Lab, very critical exercise physiology lab in the emergence of exercise science as a discipline. Dogs, Joe and Sally, ran without exhaustion for 24 hours when they were fed sweets. But without the sweets, both dogs became exhausted. So something was leading the researchers to say, hey, something's going on in terms of the availability of glucose during endurance exercise. All right. And this could be related to fatigue. Fatigue, we've talked about this in previous lectures, general tiredness or the inability to generate muscle force over time. Um, so, but here we'll use fatigue to represent that general tiredness. And this hypoglycemia at this stage really seemed to be related to fatigue. Okay, the other macronutrient I want to talk about is fats. 3 groups of fats: simple fats, compound fats, and derived fats. Simple fats are triglycerides, the most plentiful fat in the body, about 95% of fat in the body. There's 3 fatty acid molecules attached to one glycerol molecule, triglyceride. Compound fat, simple fat combined with other chemicals, for example, lipoproteins. This is used in the transport of fat in the blood. And derived fats, fats derived from simple and compound fats, for example, cholesterol. Okay, ultimately, we're really going to talk about triglycerides. Okay, triglycerides and free fatty acids are going to be the type of fat that is going to be metabolized to yield ATP. Fats are digested in the small intestines. Enzymes come from the pancreas. They're stored as triglyceride in adipose tissue, as well as in muscle. We saw that in chapter 1. But your adipose tissue is a bunch of triglyceride, a bunch of stored chemical energy. It's to be used as energy, fatty acid must be separated from the glycerol molecule. Free fatty acids and glycerol are transported via the circulatory system and carries albumin. Protein of prime importance. We actually won't talk much about proteins being used as a fuel source. However, athletes are incorporating protein in their drinks that they're using during endurance events. It may have something to do with rate of absorption of the whatever's in the drink into the circulatory system. Protein just means of prime importance. Combinations of amino acids make up proteins. 20 amino acids required by the body. 8, maybe 9 cannot be synthesized in the body. These are called essential proteins. Digested to yield amino acids. Amino acids are transported to the liver, used as an energy source during prolonged exercise, longer than 3 or 4 hours. Maybe 2 to 8% of the energy comes from protein. This might also happen if you're not eating, you're fasting, where proteins may become a bigger source of fuel for muscle contraction. Okay, we're going to stop here. This is the end of the types of fuel: carbohydrates, fats, and protein. Talked about digestion, and digestion being a complex process from chewing, mechanical, esophagus, squeezing, still mechanical, chemical, saliva, enzymes released into the GI tract to ultimately absorb carbohydrates and fats into the system via the small intestines and water via the large intestines. Okay, thank you.